Okay, so let's go over rotational kinematics here. First thing we're going to do is we're going to review original kinematics, called translational kinematics. Okay. Then we're going to talk about angular position. Okay, and after angular position, we'll have acceleration, and velocity, and acceleration. And then we're going to get into constant angular acceleration. Okay. So essentially what we're going to do is we're going to come up with a set of kinematic equations for an object that's rotating on an axis. All right, so we're going to start with linear motion. Review linear motion here. Linear motion. Okay, and for our purposes here, we're going to restrict it to just the x-axis because that's where our other ones were. But then we were able to extrapolate out into vectors. So we have a line, and here is 0, and we have a point here. We'll call this distance here. This is its position. We're going to call this x initial. And then if this moves out to a point over here, then it's going to have, it has a final position, x final. And then we know that this change in its position is, we're going to call this our delta x, and that's going to be our change in our position. And this here is our is our definition. If we do x final minus x initial, that equals our delta x, and that is our definition for displacement. All right, so there's a displacement. Now, if we have a displacement, then we know, and we take the rate of change of our displacement, we get delta x over delta t, because over the change in time. This is our average velocity. Now, we can then take this velocity, our average velocity, which we write with a bar over the top, and if we take the limit of this as our delta t approaches 0 of delta x over delta t, then we're going to get our instantaneous rate, a ratio that is instantaneous rate of a position divided by time. And this becomes our dx dt. And we can continue on with this, where we can take our acceleration, our average acceleration equals our average velocity, our change in average velocity over a change in time. And if we do the limit of that, then we're going to get dv dt. Okay, so if we take do the limit of all that, then that leads to dv dt, which equals our acceleration, and we throw our vector on there also. Now, if a is constant, then we had if our acceleration is constant, then we have a situation where, let's say we have, here's our velocity time graph, and we have this, and the slope of this line, because it's straight, it represents an average, it represents a constant acceleration. This is v, and this is t. Oh. There we go. Okay, and we know that this little change right here and that little change right there will give us, that our slope is going to be acceleration. And so we know that our velocity is going to equal whatever, well, it's the line right here. So it's whatever our v-intercept is, which is going to be v naught, plus the slope of our line, which is acceleration, times the horizontal component, the independent coordinate, which would be t, and so that's our first kinematic equation. Then we know from there that this is a trapezoid, okay, and the area underneath this trapezoid, okay, is going to give us our displacement, and our displacement equals, so delta x is going to equal the area of the trapezoid is the height of the first one times the height of one base times the height of the other base divided by 2 times the altitude, or it's the average of the two bases times the height, which in this case is t. Okay. Then if we substitute our v into this equation, we wind up with delta x is going to equal v naught t plus 1/2 at squared. And I believe if we plug in our, if we set these two equal to each other, we wind up with our v squared equals v naught squared plus 2a delta x, which is our fourth kinematic equation. And that's, okay, so that's our, that's for linear. Well, this works because we can represent our objects as dots, but when we get into rotational mechanics, rotational kinematics, we can't do that anymore. So we have to, well, let's give an example here. If we have a rotating object, like so, and this is going to spin on its axis here, so it's going to, spin this way. This is going to have rotational motion, and sure, if we have a point out here that for any particular moment is going to have a translational motion, but if it's continuously spinning on this axis, then we need to look at this in a different way. And so we're going to turn this into rotational motion. Oh, that's beyond. Okay, rotational motion. Alright, so let's say we have this blob. It's on our xy axis. And there's a point on the blob right here, and the position of that point is given by r1, and then this blob rotates, and because it rotates, this point, and it rotates about our origin axis right here, and it rotates there, it will wind up with a position r2. Alright, well, because we know this object is rotating in a circle around this point, we can start describing things in a little different way. That this right here is going to be its original angular position, and this is going to be theta 1. Zoom out here. Hold on. I'm sorry, zoom in. Okay, so right down here is theta 1, and if it keeps, when it rotates, so it starts at theta 1, but if it rotates some more, it winds up here at theta 2. Okay, well, if we have theta 1 and theta 2, and we we find our change and where it went from this angle all the way to this angle, to find the change in something, we subtract the final minus the initial, and I'm sorry, 1 minus the initial, and we wind up with our delta theta, because that's always been our definition of change, is that there should be a 1 right here. 1. You still can't see that very well because it's ugly. So 1. There we go. Okay, and this becomes our what's called our angular displacement. That is our angular displacement right there. And this, of course, can occur with a change in time, and so that would give us a delta theta over delta t, okay, which will give us our average angular velocity, and this is called omega. Okay, and yes, it kind of looks like, well, it's a W with rounded bottoms to it, rounded corners. Okay, and it is, and so that's the average angular velocity. And then if we want to find the instantaneous, we of course find omega, and we take the limit of limit as delta t approaches 0 of delta theta over delta t, which becomes d theta dt. And both of these, believe it or not, are vectors, or they behave as vectors. And it's because things spin. There's a direction to things spin. It could either be clockwise or counterclockwise, for example. And so in order to keep going with this, we need to define this according to our axis of rotation. And so here's, let me zoom out here, I'm going to show you how this works. That with this being, here's our object, and it's going to rotate this way, in this direction. Well, the way we determine our vectors, we take our fingers and we point them in the direction that we're starting, and we curl them in the direction of the change. So if we're changing our displacement, then we're going to curl this way. Okay. Let's say our if this is an increase, let's say it's a change in angular velocity. Well, if it's a change that's going faster in this direction, you know, faster in a counterclockwise direction rather than faster in a clockwise direction. If it's going this way, then we curl our fingers this way. And our vector is provided by our thumb, and this is called the right hand rule. So you have to use your right hand when you're doing this. You lefties, sorry, you don't get to use your left hand. However, you are at an advantage here because you get to write and do your work at the same time that you're testing with the right hand rule. If you're right-handed, pencil down, figure out the right hand. Okay? And that is the direction of the vector. So if things are moving in a counterclockwise direction, the thumb is pointing up, and so we'll write that as a counterclockwise. Counterclockwise equals the positive k hat direction. Okay, so if this is x, this would be I hat, right? And this is j hat. So k hat would be up this way, and this is the positive k hat direction up into the camera here. Okay, and clockwise, likewise, clockwise would be the negative k hat direction. Okay, and both of these have two different ways of looking at it. So if something's coming out of the board at you, the vector looks like, the way we draw it, we can draw a vector that looks like that. And if it's going into the board, then we draw a vector that looks like this. And these are representative of the tip of an arrow and the tail feathers of an arrow. So this is coming out of the board at you, and this is going away from you into the paper, or into the board. Okay, now I believe these are called pseudo-vectors. They don't actually behave well with standard vector addition. That you break it up into its components and go from there. That doesn't really work like that. But they are there, and they do exist because they do need to represent directions of spin. So because of this, we wind up with our kinematic angular kinematic equations. Okay, and our angular kinematic equations are exactly analogous to the linear ones. So, just as we have, okay, we'll do them over here. Just as we have V equals V naught AT, this has a directly analogous equation in angular kinematics, which would be omega equals omega naught plus alpha t, which we didn't get to over here, by the way. But omega, so we have, I should have done that first. Omega is d theta dt, and then if we do d, let's come back over here. Then if we do d omega dt, we wind up with alpha, and alpha is the angular acceleration. And these are, usually it's done in radians, but it can be revolutions as the angular displacement. we usually use radians, so radians per second squared, or radians per second, or just radians for our angular displacement. So these two are analogous equations. We're going to have delta theta equals omega plus omega naught over 2, and times t, we have delta theta equals, not mu, equals omega naught t plus 1/2 alpha t squared, and omega squared equals omega naught squared plus 2 alpha delta theta. And those equations still hold. Those are our standard kinematic equations for angular kinematics, and you can see they're almost exactly analogous to what we have with our kinematics. They handle the same thing, except it's with rotations rather than linear. So I'm going to give you an example here. Okay, so real quick, our example is going to be it's example 10.1 on page 297. So on page 297, given a constant angular acceleration of 3.50 radians per second squared, and initial angular velocity of 2 radians per second, and an initial time of 2 seconds, and we're going to see how far it spins in a total of, so our t final, t0 is 0 seconds, t final equals 2 seconds. Alright, and we are to find delta theta, our change in our angular position. Well, delta theta, what do we have? We've got time, we have initial velocity, we have acceleration, and so we're going to use our third kinematic equation. Theta equals omega naught t plus 1/2 alpha t squared, which winds up being 2 radians per second times 2 seconds plus 1/2 of 3.5 radians per second squared times 2 seconds squared. Well, this winds up being 4 radians plus 1/2 times 2 squared is just 2. 2 times 3.5 is 7 radians, and that equals 11 radians, and that's delta theta. And that's pretty straightforward, but that's how it goes. So that is our rotational kinematics, and you guys should be taking care of that for next week.